Hello, today we are going to discuss rectilinear motion. We will examine uniform rectilinear motion and uniformly accelerated rectilinear motion. Finally, Jay will present an example to clarify the concept studied. In the previous class, we saw that according to the trajectory, the motion could be rectilinear. In this case, the normal acceleration was 0. We are going to see how J moves taking into account both the trajectory and the constant velocity that we observe. Well, we are going to study the uniform rectilinear motion, which is the one that J has taken in this case. Due to its rectilinear nature, the normal acceleration is 0 since the tangent vector is constant. As it is uniform, the velocity remains constant. And therefore, its derivative is 0, and the tangential acceleration is also 0. It must be taken into account that in this type of motion, the velocity is constant in magnitude, direction, and sense. We are going to choose as J's direction of motion the x-axis. Initially, it is in the position x sub 0, and it moves in the positive sense of this axis. Being rectilinear, the normal acceleration is 0, and being uniform and having constant velocity, the tangential acceleration will also be 0. Let's see the equation that gives us the position that J has at each instant. We start from the expression that appears on the screen, separate variables, and integrate between the instant 0 and any instant t, taking into account the values of the position at those two instants. By performing the integration, we obtain that the position is a function of time where x sub 0 and v sub 0 are the initial conditions. Then we have seen that in a uniform rectilinear motion, the acceleration is 0, the velocity is constant, and the position as a function of time is given by the expression that I am pointing out. If we represent these in kinematic diagrams, that is, velocity versus time and position versus time, we see that the velocity is a horizontal line because it is constant, and the area enclosed under it in a time interval corresponds to the displacement suffered by J in that interval. If we represent the position, we see that it is a straight line whose slope gives us the velocity that the mobile has followed. Well, let's keep in mind that these magnitudes are vector magnitudes, and therefore we must express them as such. If we take that into account with the direction we have taken for the motion, and taking into account the sense of motion that we have adopted for J, the acceleration, velocity, and position will be given as shown on the screen by the unit vector, and because it is the unit vector in that direction. Let's see how J moves now. J starts from rest and will acquire a velocity that it will then maintain. Then the velocity now is no longer constant. Then, at the moment of starting the movement that J has experienced, is a rectilinear and uniformly accelerated movement. Because it is rectilinear, the normal acceleration is 0. And because it is uniformly accelerated, we will consider that the variation of velocity with respect to time will be constant. That is, the tangential acceleration is constant and equal to a. Let's see the equation that gives us the velocity at each instant. We start from the expression that appears on the screen, separate variables, perform the integration as we normally do, and obtain the velocity as a function of time. If we want to find the position at each instant, we will start from the relationship that exists between position and velocity, taking into account that now the velocity is the one we have obtained before. Well, we separate variables. X sub 0 and V sub 0 are the initial values, and A is the value of the tangential acceleration that in this case is constant and we had called A. We will represent, to continue, the characteristics of uniformly accelerated rectilinear motion. This type of motion has a constant acceleration, a velocity that depends on time as it appears here, and a position that also depends on time. And we have there highlighted, if we represent these quantities in kinematic diagrams, we see that the acceleration is a horizontal line because it is a constant acceleration. The velocity with respect to time is a line whose slope will give us the value of the acceleration of the mobile. The position versus time gives us a parabola, and the slope of the tangent line at a point gives us the velocity of the mobile at that point and at that instant. It must be taken into account that in this case, also the magnitudes with which we are working are vector magnitudes, and therefore with the choice we have made. Of direction and sense of motion, the acceleration, velocity and position in vector form. Velocity and position in vector form will be given by the expressions that appear on the screen. Well, this is the moment when J is going to pose us a problem. J is thinking, and meanwhile, he throws the ball upwards with a velocity of 6 meters per second. His hand is 1.3 meters above the ground. He asks us to determine the time it takes for the ball to reach the maximum height, as well as the height the ball reaches. The first thing we have to do is to set up a reference frame. We have chosen a reference frame with origin at the ground, and the direction of motion of the ball is the z-axis. We have taken it positive upwards. The initial conditions are that the initial velocity is 6 meters per second, and with our choice of axis, the initial position will be 1.3 meters. Since the velocity is a vector quantity, we will have to express it as such, and therefore v sub 0 will be 6 k-meters per second. We must take into account that the ball will be subjected at all times to the acceleration of gravity, which we all know is 9.8 meters per second squared. With the choice of axis, this acceleration, we will express it as minus 9.8 k. Let us take into account the equations that we have obtained for the uniformly accelerated rectilinear motion, since we see that it is subjected to a constant acceleration, and therefore the equations are those that appear on the screen. It is the moment to solve the doubts that Jay had, the time it takes for the ball to reach the maximum height. This height will be reached when the velocity of the ball is 0. If we substitute these conditions in the expression, this one here we get that the elapsed time is 0.6 seconds. He also wants to know the height that the ball reaches. Let's consider the expression that gives us the position, considering that z sub 0 is 1.3 in this case, and substituting the time that we have obtained before in this expression. Finally, we obtain that the height it reaches is 3.1 meters. Well, the time has come for Amanda to remind us of what we have studied today. We have seen the equations of rectilinear and uniform motion. We have also seen the equations of uniformly accelerated rectilinear motion. These equations have been obtained considering that the motion took place along the x-axis in the positive direction. Amanda also reminds us that these quantities are vectors, and therefore we must express them in vector form. Well, that's all. See you in the next class.